Yes, so we consider a simple complex Lie algebra G. Simple complex Lie algebra, and I want to find a real subalgebra GR in G, say that G is complexification. I said last time, and I want to make it even more clear now, that to find such subalgebra we need to find something else. Namely, we need to find an anti-linear automorphism. Lie algebra automorphism of G says that its square is the identity. You should think of this as of the complex conjugation. And then GR is simply the set of fixed vectors. Sigma, the real dimension of this is the same as the complex dimension of G, and everything is true. Actually, it is not hard to prove. I don't want to discuss it today, that there exists one-to-one correspondence between what? Real forms. This subalgebras GR in G are called real forms. So there is some equivalence relation between them. And then natural equivalence relation. And then just the conjugate classes of such automorphisms. One-to-one correspond to all the real forms. So there exists a classification of all real forms. And at least in the classical case, these real forms are sort of all well known. Some of them are well known, some of them are just known. So what are the real forms? Let me begin with the most visible case. Consider the complex Lie algebra ON. I mean, orthogonal. The group is the group of complex orthogonal matrices. The Lie algebra is the Lie algebra of skew-symmetric, not skew-symmetric, skew-symmetric n cross n complex matrices. What are the real forms? I want to say that at least, well, one of them is obviously known. Just take O and R. Just take the real orthogonal, real symmetric matrices. This Lie algebra is a Lie algebra of a compact Lie group, and that's okay. Can you think of other? You can, but?
Different signatures? So
different signatures. OPQ. So you can, you can take N, present it as the sum of P plus Q, where P and Q are both positive integers, and then consider O, P, Q, certainly R. In the complex case, no such thing. So what is ON? I mean the group ON. The group of transformations which preserve the form, the sum of the squares of coordinates or some other positive definite, negative definite form in the space Rn. And there are, as Colin says, forms of different signatures. So OPQ, what is this? If you want to present it as the algebra matrices, this will be symmetric. So we should and also BT is C, not negative C. If BT is negative C, this is simply symmetric matrices. So this is a matrix description of the Lie algebra over PQ. It is certainly a Lie algebra, certainly Lie group, which is not compact. Yes. Do you think, speaking of real forms of the Lie algebra ON, do you think it is all? Or there is something else? I don't know. There exists actually one more construction. I will discuss it, if not here, then in my notes. There is some quaternary construction. So I can say unitary quaternary matrices. Just one more. It appears only when n is even. If n is odd, then this is all. Now, SL and C. Certainly again, there is SL and R, and there are, similar to this, U, PQ. Such unitary matrices which, I mean a Lie group, unitary matrices which preserve a Hermitian form of this signature PQ. And the corresponding Lie algebra, which can be easily described in a similar way. This is also, all of them, this and this, are real subalgebras of this, and the dimensions are the same. The fact is that it is almost full set of real forms of SLC. Again, if n is even, there is one more. Such quaternary construction, which can be denoted as SL. It is very easy to describe this Lie algebra without any quaternions. After all, this is a algebra of this. Very similar for SP. You know less about SP, well, you maybe know a lot about SP, but I said less about SP here. So I also can say that there is such a thing as SP PQ. And nothing else, actually, in this symplectic case. I want to say that of this Lie algebras, only one is compact. It is UN. If P is n and Q is 0, here P plus Q is n. Compact Lie algebra, real Lie algebra. I said that last time, and I proved something last time. I don't want to repeat at least the proofs. So a simple complex Lie algebra, compact real Lie algebra is just a real Lie algebra whose killing form is negative definite. That's all. And the fact is that a real Lie algebra is compact, more or less even on leaf. There are, well, even on leaf certainly, but there are some additional statements. Even on leaf, it is the Lie algebra of a compact Lie group. So compactness has a very natural geometric sense. Yes. Now, a theory which I formulated last time, and we began proving it. Probably I need to discuss this proof in more details now, although my time is limited. This is the fact, theorem. Every simple complex Lie algebra has a compact real form. Actually, this compact real form is unique in some reasonable sense. There are some further statements which I will discuss, if not here, then in my notes. But now just this theorem of existence. So again, theorem. There exists a compact real form for every complex simple Lie algebra. You should understand that actually this theorem, maybe you can look at this theorem from different points of view. For example, suppose that you have some real Lie algebra or real Lie group, very much not compact. Then what? So real Lie algebra, if we speak of Lie algebras. Then what? You take this Lie algebra, you complexify it. It will be a complex Lie algebra, right? Now with this complex Lie algebra, also simple. You find a compact form. So this construction gives you apply it to some real, say simple, semi-simple Lie algebra, and you get another real semi-simple, simple Lie algebra, which has the same dimension. And almost the same Lie algebra. I mean, the Lie algebras, they certainly are not the same. But they have the same complexification. By the way, if you are interested in this subject, also the same cohomology. Yes, so these Lie algebras are very much related to each other. Say SL2 and O3, two three-dimensional Lie groups. I mean SL2R. What do they share? More or less nothing. Certainly the maximum compact subgroup of SL2R is a circle. It's contained in SO3, it is also SO2. But still they are very much different. Both are three-dimensional. This is certainly what makes them sort of similar. But they have the same cohomology, I mean the Lie algebras. And also the groups have many similar properties. Groups also may be complexified. There exists such an operation of complexification of, if you wish, real analytic manifolds. So real analytic groups. So for real analytic groups you also can speak of complexification. And these two groups, SL2R and O3, SO3 better to say, have the same complexification. This is SL2C, which makes very similar many their algebraic properties, without any similarity from the geometric point of view. So for the group SLNR, which is very much not compact, the group UN, SUN actually, well I didn't write this S, SUN certainly, the dimension should be one less. As the group SUN is this compact form. So this Lie group very much different, but they have the same dimension, squared minus 1, and the same complexification, which makes their algebraic properties very similar. I hope it is. I said what I wanted to say clear. Now let me return to the proof of existence of compact form. It involves some computations. I hope I will be able to show them to you. If not, otherwise we'll have to do this. So we're written in my notes. It's not written so far. It's not yet. Yes. It is written. No, I don't remember. Probably not. Probably not written so far. But I will write it. So we have theorem. You understand? Again, theorem. Every simple complex Lie algebra, and this is G, has a compact real form. So it's a complexification of some compact real algebra, subalgebra of this. First of all, I want to remind you, we discussed it several times, maybe even last time, such a thing as while basis. G is this sum, and First of all, G alpha. We can certainly what we can do. We can choose E alpha in G alpha, and we did it here. Say that E negative alpha, E alpha, this commutator, is equal to minus H alpha, which is equivalent to the fact that the inner product of them is -1. You remember there is a formula for the commutator of any elements of G negative alpha and G alpha. So we have this. If you have under these conditions, then certainly this E alpha is chosen very much not uniquely. You can multiply E alpha by any number and multiply E negative alpha by the opposite to this number, and you will get another pair with the same properties. But there is a map evolution of the set of roots of G, known as delta, into delta again, which takes any root alpha and negative alpha. Certainly this map preserves everything which it can preserve in the product. I don't know what else. By this reason, there arises a map, Lie algebra automorphism, G into G. It is linear, not nonlinear. Lie algebra automorphism, which takes G alpha into and certain H into H. Now I want to choose this E alpha in such a way that omega of E alpha is equal to E negative alpha. It is very easy to understand how to do it. You have some choice. I now prefer to write that this is E prime alpha with these properties, with the prime notation, the prime notation. And now omega of E prime alpha is equal to E prime times some complex number rho alpha. I can say rho alpha, rho negative alpha is rho alpha inverse. It should be because of this property. Then simply write E alpha is equal to rho alpha to the power minus 1/2 E prime alpha. Now if you write this equality and also the equality, this equality, and so also E prime alpha is equal to rho alpha, right? You will immediately see that this will become omega of E alpha. So this rho alpha disappears. Believe? It is very clear. It will appear twice. This will appear twice and cancel this unnecessary thing. So this is called the Weil basis. Not in G precisely, in so far in that part of G. Then you may remember that we used these E alphas to produce N alpha betas. You remember E alpha, E beta, if alpha plus beta is a root, is this. If alpha plus beta is not a root, we just put it equal to 0. Yes, I did this all, and made some computations. We did it when we wanted to prove, this was written in my notes. We wanted to prove that Dinkin diagram, that the root system, fully describes the isomorphism type of the Lie algebra. So if two simple complex Lie algebras, say, have the same Dinkin diagram, then they are isomorphic. Yes. Now, if I choose the vectors E alpha under this condition that they are taken into each other, that E alpha and E negative alpha are taken into each other by the automorphism omega, by some automorphism of the algebra, then immediately I have the following. So for Weyl basis n alpha beta is equal to n negative beta. Obviously, since E alpha and E negative alpha, E beta into negative beta, E alpha plus beta and E negative alpha minus beta, they are related by an automorphism of Lie algebra, so certainly the commutative relations also are preserved. From this, I want to deduce something. If you still remember, we had the following relation, even without this property. We have the following relation. Don't need to explain what Q and P is. They come from the structure of the root series. Don't you remember? Remember. It's negative side. Yes. But this right-hand side, as far as I understand, is a positive real number. Alpha is a positive rational number. Well, let's be real, but still positive. Q in 1 minus P, also very much, it is non-negative. So this is a real number, and if it is also n alpha beta squared, in this case, then I can say that n alpha beta is real. It will be important. So for the Weyl basis, these are real numbers. Actually rational. Are they? No, square roots. I'm not sure. I'm not sure. Square roots. No. Their squares are rational. It is clear from this formula. They are not. Now the next thing which I want to say. Well, there are also some other things which are real, and we proved this many times. Some time ago. Say, in the product of roots are rational numbers, so, hence real numbers. This, for example. Now, I did this last time and I repeat it now. How to define the compact Lie form? We do the following. We take our Lie algebra G, we take Weyl basis, and also, if you remember, in H, we have the real part. This is the set of all real linear combinations of the vectors H alpha. Also, it's possible to do actually also over the field of rational numbers. I don't need it. I take this and I choose a basis, H1, HR, in H, but the vector should be real. You understand? So they are real linear combinations of root of H alphas. And then I do the following. I take an element of G, and this is this thing, right? An arbitrary element of G. So G E alpha r is a well basis. This is this. And then my transformation sigma takes this into the sum minus mu I bar hi plus the sum alpha lambda alpha bar e negative alpha. Okay, and now the computation, which I'm going to provide now, at least, well, I hope to be able to explain it in full. The computation, well, it is very tempting to say at this moment that the computation is sort of immediate. It is, although it's sort of longish. And it shows this information. Well, I even do not mention the fact that its square is identity. It is too obvious from this. But also, first, it is a Lie algebra automorphism. And second, the space of fixed vectors for this transformation. It has to be a real subalgebra of G if this is an automorphism. But what I want to say, that the restriction of the Killing form to this subalgebra is negative definite, which shows that, yes, we have this real structure, this complex conjugation, real structure, which shows that the given Lie algebra is a complexification of some compact real Lie algebra. Questions at this moment? No? Good. So again, the fact that the square is the identity is visible from the definition. If you apply it twice, you get what you had. I want to maybe to write it even here because so when this thing is fixed by sigma, very obvious, you should have mu I as equal to negative mu I bar. If you really prefer, you can say that mu I is purely imaginary, right? And also lambda alpha bar is equal to lambda negative alpha, yes. Right? Well, even if it is wrong, it will show itself at some moment. Good. So now, two facts. One is immediately obvious. One is sort of obvious after you pronounce several words. Very simple. This transformation sigma is a Lie algebra automorphism. Since this transformation is at least linear after real over reals, well, anti-linear, we can prove that the commutators are preserved for the summands in these sums. Take this mu hi mu prime hj. This is from the first sum. And apply sigma to this. Or take sigma mu hi sigma prime hj. These two things are equal to each other mostly because they are both equal to 0. Everything is within h. H is commutative. I understand what you want to say. That it is even too easy to prove. Now, the second thing, sigma lambda E alpha mu for lambda prime E beta, or also not too hard. This is sigma. Well, lambda and lambda prime, so we just have their product. And then when we apply sigma, it becomes lambda bar, lambda prime bar. So we can forget about lambda. Same here, by the way. And then you should take sigma and apply it to the commutator of this and this. And this is n alpha beta E alpha plus beta, right? Well, this is the definition of is. And this is lambda bar, lambda prime bar, and alpha beta bar. E negative alpha, negative beta, right? Wonderful, this thing. Again, lambda and lambda prime, they certainly, when we apply sigma, they become the conjugates, and when we apply the commutator is linear. And here I need to write what? E negative alpha, E negative beta, sigma of E alpha and E beta. And this becomes lambda n negative alpha negative beta, E negative alpha negative beta, right? And these two things are the same because of the two facts. N's are real, and n alpha beta is equal to n negative alpha negative beta. Nothing else to say. Now the last thing. What if we consider sigma of mu hi lambda E alpha, or sigma mu hi sigma lambda E alpha. Again, I want to prove they are the same. Again, this is immediately true. As to lambda and mu, they again, lambda and mu become lambda mu, and when we apply sigma, so this is lambda mu both bars, and then sigma of what? Of hi E alpha. Very interesting. And here's the same. Lambda mu, and I apply sigma to hi will be negative hi, right? I apply sigma to E alpha will be E negative alpha. You see, h E alpha up to the sign minus alpha of h. H here, hi, is a real vector, a real linear combination of h alphas, which means that when we apply E alpha to it, we get alpha of h, which is a real number. There is a formula for it, if you prefer. Actually, if this is h beta, this is simply the inner product of alpha and beta, which is rational, real, real for h. And then these things become the same. You see, this becomes alpha of hi minus, well, minus will be here and here, so maybe you can forget about it. And this, when you apply sigma, then E alpha. When you apply sigma, then this alpha becomes E negative alpha. And here we already have E negative alpha, so the equality between this and this immediately follows from this, and the fact that all values like this will be real in our situation. already. It is an automorphism. Any remarks about this? No remarks. It is slightly more work to prove that the restriction of the killing form to the set of fixed points is negative definite. What's negative definite? That is the inner square of an element is negative, right? Since we consider a set of fixed vectors, we can actually take the following. We take an element G, and then we consider certainly the product G and G, but since G is equal to sigma of G, it is more convenient to consider this. And to prove this is negative. By the way, the proof itself shows that not only this form is negative, which is certainly true, but also we can consider now Hermitian form on the whole the algebra, not on the fixed part. Defined by this formula. So we can write B of GH is equal to the killing product of G and sigma of H. Since sigma is an anti-isomorphism, this becomes a Hermitian form actually. And this Hermitian form now can be positive, definite, negative, whatever. And actually, this is negative definite. And my proof, for which I have 7 minutes, actually shows that. I will not specify this precisely in the process of, of the proof. Moreover, it may be not very much visible, but it is so. Actually, what is true, what is proven by the computation which I am going to present now, is the fact that actually this real structure, this complex space with in the product, gives you a Hermitian form, a very common construction in linear algebra. And this Hermitian form is negative definite, which is precisely what I'm going to prove. Now, still I want to prove this. So G is fixed by sigma. So I consider this thing mu I h I plus the sum lambda alpha e alpha, comma, negative mu I bar h I plus the sum lambda alpha bar e negative alpha. And I want to prove that this, provided that mu i's are purely imaginary, you remember, and lambda alpha also satisfies some condition, that this is a negative, real negative number. This number is no, because you know that 2 times 2 is 4, consists of 4 things, right? For this, denote this as h, denote this as sigma h, and the first summand is h sigma h. This is a negative number. Why? Because this is equal, according to our rules, these are elements of the Cartan algebra, alpha of h times alpha sigma of h, right? What is alpha sigma of h? So alpha, what is alpha of h, first of all? It is the sum mu I alpha of hi. What is alpha of sigma h? It is the sum minus the sum mu I bar alpha of HI, right? And then also it is true that mu I bar is okay. Sigma of H is this sum. Yes, I apply alpha to it. So I get this. Because I wanted to say that actually alpha sigma of H is alpha of H bar. That alpha sigma of H is alpha of H bar. Is it really seen from this? If it's not seen from this, then
Yeah, because the roots are real, right?
yes. So I wanted to say that this is always true. Yes, but certainly if these numbers are real, alpha of H, then simply this is the sum. They're simply equal to each other. And this is the sum of alpha H squared, yes. If we assume that H and sigma of H are equal to each other, then simply so these two numbers are equal to each other. Because mu I bar is negative mu I, right? Yes, so simply we have this. It is sufficient to say this. And this is minus, 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 minus. Should minus this. Very much excuse me. It should be okay. And if it is not okay, is by some very stupid reason, which see something? No. So let me, since I have only 2 minutes, probably I anyhow will. I didn't want to do that. To return to it later. What I so this it should be minus alpha of H. Yes, it should, so I will make corrections next time. So now I cannot say much more. The inner product of this and this also should be negative. As to the other two inner products, this and this and this and this, they cancel each other. They are the same. They will cancel each other. By this reason, this thing is negative. So I will provide corrections to this proof next time. And now I just want to say some very last thing. Is there a classification of all real forms? I'm not sure that I will be able to return to this. And how to find this classification for a given simple Lie algebra? It is done in the following way. First, we notice that actually the classification of antilinear automorphisms of a simple complex Lie algebra is the same as the classification of linear automorphism with square 1. And this is by the following reason. A simple theorem states that, well, this is the involutions which we consider, the antilinear automorphism with square 1, may commute with each other. It may happen. Suppose that sigma and tau are two such maps, then sigma tau is also the product, is also involution. But since sigma and tau both are anti-linear, product I mean composition. Since sigma and tau both are antilinear, their composition will be linear. And now the fact is that for any real structure, for any involution with our properties of a simple complex Lie algebra, there exists a unique compact involution which gives which has this compactness property, which commutes with our involution. So we have involution sigma. We find another involution tau which commutes with this, and it is found by some unique procedure. And we take the composition sigma and tau, or tau and sigma. They commute, and then you transform an involution of and a linear involution of simple algebra into a linear involution. And linear involutions are fully classified. And this is an algebraic thing which is done without much difficulties. So I thought it was all okay, but now probably some minus here is should be removed. So certainly there should be a minus. And I will do this next time. I hope not to spend too much time on it next time. So see you.